For today, we're going to extend on what we did yesterday, right? So yesterday, we talked about how to do absolute value equations that looked like this, where we were able to get an isolated absolute value expression on one side, and on the other side, we ended up with a number, right? And we knew how to deal with that. No big deal. Everyone was fine. Today, we're going to look at things, something a little different, an extension of that. So what happens if we have a problem like that? It's different. This time I've got an absolute value expression with variables in it on one side and an absolute value expression with variables on the other side. And the good news is we're going to use the same strategy we used before. And here's why we can. Because we know that regardless of the sign that these expressions give us, whether it's positive or negative on both sides, because they're all in absolute value expressions, they're always made positive, right? And so there's a couple things, couple cases we have to consider. What if 3x plus 2 is exactly equal to 5x minus 8? Well, then we would do what we normally would do. We would just set whatever's inside the first absolute value bars equal to the positive of what's inside the second set of absolute value bars on the right. That's one possibility. What if, though, 3x plus 2 is equal to the opposite of 5x minus 8? It's still going to work, because if one of them is negative and one is positive, the absolute value bars are going to make the negative one positive anyway. And so the other case we would consider is if what's inside the absolute value on the left is equal to the opposite, the negative of what's inside the absolute value on the right. Isn't that what you would have anticipated, though? Based on what we did yesterday, that's the same pattern we did yesterday, right? We just set whatever's inside the absolute value bars equal to the positive of what's on the right or the negative. Same strategy.
Why didn't you just set it up, though, just opposite of each number?
So you distribute the negative. Yeah, you would. Exactly, yeah. So when we solve these things, what do we get? We distribute the negative on this side, so we get negative 5x plus 8 on the right side in our second equation. And then we're just going to solve these things. Now, we would normally, I don't know why they did this, we would push the x's to the right. For some reason, they didn't. They pushed them to the left. They subtracted 5x from both sides and got negative 2x. Then they subtracted 2, but whatever. I mean, we're going to get the same answer. We get x equals 5 from the left equation, first equation. And if we solve this one, we would just add the 5x back to the left side and get 8x plus 2 equals 8. Subtract 2, and I get 8x equals 6. Divide by 8, and I'd get x equals 6 over 8, which would just reduce to 3/4. Okay, no big deal, right? You guys can do this. Try one. Go try that one real quick. So that was good. I like what I saw. So first thing we did was we split this into our two equations, and I thought everybody did that correctly, right? So either what's inside the first absolute value equals the positive of what's inside the second, or it equals the negative of what's inside the second. If I solve this one, I'm just going to add x to both sides, add 3 to both sides, get 2x equals 8, so I get the solution x equals 4. There's a solution. How about on this side? I distribute the negative, and yikes. At this point now, if I subtract x from both sides, don't I just get negative 3 equals negative 5? That's false. That's false. So that's telling us that this one, the second equation we built, has no solution. So how many were there? How many total solutions were there? Just one. Just one. That time we only got x equals 4. Okay, no big deal. You guys have got this. So now we're going to look at one like this. How is this different? What do you notice about this one that's different than the last one we looked at? Okay, there's no absolute values around the variable on the right side. Well, no, but it makes a big difference. It makes a big difference. So the stuff that the ones we just looked at, these were the two examples we've done today so far. Examples like these. An isolated absolute value equals a positive number, right? Gave us two solutions. or we have an absolute value expression equal to another absolute value expression. So in both of those cases, they're similar in this way. Any solutions I get are guaranteed to work. If I get a solution, checking it is sort of optional. I'm only checking it to see if I maybe made a simple mistake like on a test. Okay, but when we do a problem like this one, checking is not optional, as we're going to see. So let's do this equation. What do you think we're going to do here? Because your intuition is going to guide you correctly. How am I going to split this? So what's inside the first one, right? So this stuff right here is either equal to, it either equals just that, right? So it's either going to equal positive 5x plus 12, or it's going to equal negative the right side, negative the quantity 5x plus 12. Everybody, doesn't that make sense? Those would be the two equations we would split this into? Based on the patterns we've been following. Okay, so let's solve these. How about this guy over here? So if we subtract x from both sides, to move the x's to the right, we'll go ahead and subtract 12 from both sides to move the variables to the left. So we get 4x equals negative 16. So what's the solution then? X equals negative 4. Okay, that's one possible solution. Okay, but I say possible here. As we're going to see, when we don't have absolute value bars around a variable in an absolute value equation like this, wonky things can happen. How about this other one? Okay, we'll try this guy. We distribute the negative, and we get x minus 4 equals negative 5x minus 12. So we're going to add 5x to both sides. So the x's go left, so we're going to push the numbers to the right, add 4 to both sides. And we get 6x equals negative 8. I divide by 6, right? And I get x equals negative 8/6, which I could reduce to negative 4/3, right? Well, no, we'll see. It could work. It's possible it could work. Just because the x's are negative doesn't mean that it's necessarily going to give us a negative value on the right, because that would be the problem, wouldn't it? Everybody agree? What's dangerous about this equation compared to the last one is, because I've got no absolute value bars around the pink expression, if I plug in a value of x that makes that negative, that's impossible, because I can't have an absolute value equal to a negative number, right? So we could get some solutions that don't work here. We call those extraneous solutions. We have to always check for those. Extraneous is just a fancy math word for false. Solutions that we calculate but don't actually work. So let's try this. We're going to get a little practice using Desmos, and you're going to do this in just a second. So if we go to Desmos, okay, and if I want to check this thing, we know how to do this, right? I just set f of x equal to the expression to the left of the equal sign, g of x equal to the expression on the right. So f of x is equal to, everybody agree, it's just the absolute value of, of x minus 4. Everybody agree that's the right? G of x is equal to plain old 5x plus 12. And then I'm going to plug in my solutions and see what works. So f of negative 4 gives me back positive 8. Okay. G of negative 4, what's it give me? Okay, so that's telling me if I plug negative 4 into that equation, I'm getting 8 on the left side and negative 8 on the right side. So is negative 4 a valid solution? No, it's extraneous. Okay. Let's try the same thing with my other solution, which was negative 4/3, right?
Correct.
F of negative 4/3 gives me 5.3 repeating, which I could make into a fraction if I want to. G of negative 4/3 gives me the same thing. So is negative 4/3 a valid solution?
Yeah.
Yes, it is. Okay, so then, oops. So then that tells us, so here's what we just did, right? So this is telling us that because these two are not equal, the left and the right side, it means no, this is extraneous. We have to cancel it out. But because we got the same numbers on the left and the right when we checked this one, that one is valid. Okay? So the moral of the story then is, if we're doing absolute value equations where we have an isolated absolute value equal to a number, or if we have absolute value bars around both sides of the equation, we have variables on both sides, but they're both protected inside absolute value bars, any solution we get is guaranteed to work. I don't have to check. It's optional. But if we have one like this, where I've got variables inside an absolute value on one side and not in an absolute value on the other side, then it's not optional. I have to check for extraneous solutions because often there'll be false solutions there. It might even work out that we get two solutions and both of them fail. They might both be extraneous. So there are no solutions. Could work out. Okay, so try one of these and then I'll let you work. Go to the boards and try that. One person, bring a Chromebook so you can check for extraneous solutions on a Chromebook.